Hey everyone, welcome to today's Explainer. So, today we are tackling a challenge that literally every developer runs into at some point. The dreaded, well, it works on my machine dilemma. Right? We're going to take a super simple piece of local code, completely rip it off your laptop, and actually get it running live on the public internet. And we're going to do this using one of the absolute most powerful orchestration tools out there, Kubernetes.
To get us there, we've broken this whole process down into a neat 5-step pipeline. We'll start with coding the simple app, move into boxing it up with Docker, creating the actual Kubernetes cluster, setting up our deployments, pods, and services, and finally, routing traffic out to the whole world.
All right, let's dive right in with step 1, coding the simple app. So our starting point here is a really basic Python application. It's built with Fast API and the Unicorn web server. Now, right now, on your laptop, this runs perfectly fine on localhost port 8000. But if we want to move this into the cloud, we basically have to completely shift how we think about it. We're moving away from that direct local access and preparing for an internal cloud networking setup. Eventually, this whole thing is going to operate on standard port 80.
Which brings us to step number 2, boxing it up with Docker.
See, the thing about Kubernetes is that it only really knows how to run containers. So we've got to treat our Python code exactly like a standardized shipping box. If you look at the Docker file sequence, there's a very specific logic happening here. We copy the requirements.txt file and run pip install entirely before we ever touch the actual source code. Why do it in that order? Well, it all comes down to caching. By packing those really heavy dependency boxes first, we're basically tricking Docker into caching them. And that is a total game changer for speed because it dramatically cuts down build times whenever we go in and tweak our app code later.
Okay, so once that container image is built and properly tagged, we need to do a Docker push. We're taking that tagged image and pushing it straight up to a public registry, something like Docker Hub. This step is absolutely crucial because it makes our nice little standardized shipping box universally accessible. It just sits out there on the internet, patiently waiting for our cluster to come along and pull it down.
And that leads us perfectly into step 3, creating the Kubernetes cluster itself. So if Docker is our shipping box, you can think of Kubernetes as this insanely intelligent warehouse manager that decides exactly where all those boxes need to go. The source material for this explainer uses a Kubernetes cluster on Civo Cloud, which is awesome because it brilliantly highlights the real magic of clustering, specifically the number 3. See, this cluster is actually backed by 3 individual virtual machine nodes running in a data center somewhere. But Kubernetes seamlessly abstracts all of those underlying machines completely away from us. We get to just interact with the whole thing as one unified environment. Pretty cool, right?
All right, our warehouse is ready to go, so let's move on to step 4, deployments, pods, and services.
Now, I want to slow things down just a second here because we really need to decode some of this crucial Kubernetes jargon. These concepts are how we actually tell the cluster what to do. So let's start with the pod. The pod is literally the smallest deployable unit in Kubernetes. Think of it as a super tight, immediate wrapper right around our Docker container. Now, containers inside a single pod actually share local networking. But here's the secret. In practice, we almost never create or interact with pods by hand.
Yeah, instead of manually managing those pods, we use something called a deployment. A deployment is a higher-level resource, and it essentially acts as our ultimate instruction manual. We hand this manual over to Kubernetes, and it tells the cluster exactly which container image to pull down from Docker Hub, what our configuration should be, and exactly how many copies of those pods it needs to keep alive at all times.
And let's actually revisit that number 3 for a minute, this time looking at our deployment. This right here shows off the incredible scaling power of Kubernetes. By literally changing just one single line in our YAML file, we can instruct the deployment to maintain 3 identical, highly available replicas of our Python app. If one of them suddenly crashes, boom, Kubernetes instantly creates a brand new one to replace it, which means you are not getting a frantic pager alert at 2 a.m. to go restart a server.
This whole setup also handles resource management incredibly well. If you look at the deployment's YAML configuration, you'll see it strictly separates requests from limits. Requests are the absolutely guaranteed resources our app needs just to function, say 200 millicores of CPU and 300 megabytes of memory. But the limits? Those are the hard ceilings. By setting a memory limit of, say, 400 megabytes, we make absolutely sure that if our simple little app develops a massive memory leak, it just gets terminated locally before it can take down the entire node.
Now, because those pods can crash and be replaced basically at any moment, their individual IP addresses are totally ephemeral. They are constantly rotating. And that right there is exactly why we need a service. The service acts like an internal traffic cop or a load balancer. It gives us a single, completely stable network address on port 80. So even if a pod dies and gets recreated behind the scenes, internal traffic still reliably finds the application without missing a single beat.
While we're configuring all this, our source material really leans into the 12-factor app methodology. A huge core tenet here is strictly decoupling your configuration from your actual source code. So by injecting configurations at runtime using dynamic environment variables, like setting an env variable to Civo, for example, we can entirely change how the application behaves on the fly. And we can do that without ever having to touch or rebuild the underlying Python code. It's super powerful. All right, let's take stock. Our code is containerized, it's deployed, it's highly available, and it is running brilliantly on our internal network. But this brings up a massive question, doesn't it? How on earth does the outside world actually reach it?
To solve that final hurdle, we've arrived at step 5, routing traffic to the world.
Basically, we need to configure a gateway to securely expose our app to the internet. In the Kubernetes world, this is handled by something called an ingress controller. You can think of the ingress controller, the example uses one called traffic, as the literal front door of your cluster. It reads incoming external web requests and intelligently forwards them right to our internal service, all based on the URL paths or the subdomains that we've defined.
So let's walk through this final connecting sequence. Step 1, we go in and retrieve the raw external public IP address right from our cluster's admin panel. Step 2, we jump over to a DNS provider like Cloudflare, and we create an A record. And step 3, we map a friendly, readable subdomain directly to that raw cluster IP. And just like that, external web traffic knows exactly how to find our cluster's front door.
Now, to prove this whole pipeline is genuinely working end-to-end, the source material walks us through one final proof of concept. The Python code is tweaked just a tiny bit to dynamically return its internal pod hostname right to the web browser. But because we actually altered the source code this time, it requires us to run a fresh Docker build and generate a brand new image tag iteration.
And this brings us to the strict update loop that you always have to follow. We have to treat those container tags as completely immutable, meaning we always increment to a new tag whenever the code changes. After that, we reapply the deployment YAML to trigger a really smooth rolling update across the entire cluster. Now, we're doing this manually for the sake of this explainer, right? But honestly, executing this slow loop by hand quickly highlights exactly why automating the whole shebang with CI/CD systems is the absolute industry standard.
But hey, look at this final result. It is totally triumphant. Because we updated the code to display that hostname, we get to see the load balancing happening in real time. When we refresh the live public URL, it actually returns different hostnames. Refresh 1 goes to pod A, refresh 2 gets routed to pod B. This is the perfect proof that our service is flawlessly distributing external internet traffic across all 3 of our pod replicas.
I love how the source material summarizes this. It says, Kubernetes allows me to abstract those virtual machines away, and I can just interact with them as a single cluster. Honestly, that perfectly captures the ultimate value proposition we've been exploring today. We took this complex, messy infrastructure and literally transformed it into one clean, unified API for seamless, highly available deployment.
So, we have successfully conquered the manual deployment pipeline together. But I want to leave you with one final thought today. Look back at everything we just built step by step. How much of this entire process could we automate to eliminate human error completely? Honestly, answering that question and diving headfirst into continuous integration and continuous deployment is exactly where your journey into the cloud goes next. Thanks so much for exploring this with me today.